Hello and welcome to a new episode of Rudy's Electronics Lab. And today I want to talk about an exciting new addition to my lab, which is the Anritsu MG3700A Vector Signal Generator that I purchased recently. That I'm going to talk about this device here today doesn't mean, by the way, that I'm stopping with my series of videos on the Rohde Schwarz SMIQ. If that was what you're interested in perhaps today, there are still some of these episodes in the planning. But now to the Anritsu. So in today's videos I want to tell you a little bit about why I bought this device, and for this we have to dig a little bit into the architecture of vector network generators. I want to talk about a little bit the way that the device is implemented and its feature set, and of course then we're going to do some hands-on experience. First, getting into the architecture then of vector network generators, and I would like to start with talking about an analogy with electronic musical instruments, with what is commonly called synthesizers or keyboards, because there you have two different types of devices, and to look at them can be rather helpful also in understanding vector signal generators. So what do we got with synthesizers? We have what we call synthesized devices, and we could call that real-time, or we have samplers, which actually we could call arbitrary signal generators. Now, a famous example of a synthesizer, analog synthesizer, would be the Moog. Here you see a picture of the Mini Moog from 1971 by Bob Moog, a very famous instrument. It generates basically all the signals by oscillators, filters, and other type of circuitry, ADSR for example, which is present in the device. Then a bit later in time, talking about the 1980s or so, a new type of instrument came on the market, and that type of instrument was called samplers. The very first one were from companies like Sinclair and a couple of others, and it kind of got popularized, I think, with the device you see over here. This is the Emulator 2 by MU Systems, released to the market in 1984, one of the first affordable samplers on the market. The earlier ones were basically a room full of equipment. I already mentioned Sinclair. There was another one. Can't think of it right now. I'll put it in, add it to a text later on. The two famous synthesizers of those times. And basically, what the sampler does is play back a set of pre-stored value from a memory, and you still see this device having 5¼ inch disk drives where the music file was being stored. In musical instruments, we still have kind of this distinction now. The analog synthesizers basically got replaced by what we now call like virtual modeling or virtual analog type of devices. A popular one is the Clavia Nordlead. That's one I've been playing on quite a bit. A very recent one is the Expressive Osmose that you see in the bottom. The sample is interesting. They hardly exist as a standalone device anymore. These days they're usually pieces of computer software, so we don't see so many hardware samplers anymore on the market. Now, so far about musical instruments and real-time devices versus samplers. Now if we turn this to vector signal generators, we can kind of distinguish the same two types of devices. And what are the relative pros and cons here? The real-time device or the synthesized device is very nice because you got an instant change of parameters. You go to the settings of the device, you turn some buttons and dials, and right away you change all type of parameters that you're interested in, like on an analog synthesizer. And what is also nice, especially if we talk about instruments that might be 20 years old already and there's not the support anymore, they're completely independent. They're self-alone, self-sustained. You're not depending on computer software that might not be available anymore or might not run on a modern operating system anymore. You don't have to build sandboxes or get far into the past, etc. You really got a standalone device that kind of works right out of the box. But then what are the advantages of having an arbitrary type of vector signal generator? Now, one of the clear advantages is that this device is going to be flexible. You can create all types of waveforms, also waveforms that were not originally envisioned at the moment that you bought the device already implemented there. You're also not limited to a specific modulation method. So later, if you would get interested in, say, ODFM, in principle you will be able to play that with an arbitrary vector signal generator, as long as if the bandwidth, etc., and the memory depth is enough for your purpose. And it also allows for later support of specific telecommunication standards that were developed after the device was released. You could be adding that with software. And it is those particular advantages that I got interested in getting a vector signal generator. Also actually talking with one of the subscribers to my channel, which also has a device like that, and we're exchanging some information, and we might actually do some experiments together in the future, so stay tuned to that. But I'm going to be focusing on the Anritsu. Now, what options did I consider when I wanted a arbitrary vector network generator, vector signal generator? Well, first of all, I was looking at my Rohde Schwarz SMIQ 3 that I got over here. Actually, one of my favorite devices. So this is a synthesized, you could say, device, a real-time device. Really, there's a lot to like about it, and I've been talking about it in several episodes already. But out of the box, it does not by standard have a way to have a sample memory and be able to play arbitrary files. You need some options to do that, including the SMIQ B11 or B12 options. These options are rare. They're hard to find on the market, and if I find one, they could be very expensive, and I really wonder if I still get it to work and whether I get the right software on my computer and get it to work as well. So I wasn't too enthusiastic about that scenario of extending my SMIQ here. Now the other option I was thinking about is actually the device here on the top, which is my Rohde Schwarz ARB-based I think that's what you say it, a device that came much later on the market. As you see here, it's a device from 2007, so more recent than the SMIQ. This is a baseband generator as well as a fading device, but almost all the units that you can find secondhand on the market only have the fading part and don't have the baseband generation part. And same for me. I would also need to get specific options basically to be able to play back waveform files. And in this case, I would have needed options CMU B9 or B10 or B11. Also, these options are hard to find, and they might be rather expensive if I manage to find one. On top of it, and I know this is going to be a bit of subjective, but my AMU never got that much love, really. I mean, even if it might be the most advanced device here in this kind of category that I got in my lab, nah, it's not my favorite device. I didn't really feel strongly about upgrading it. And again, I would need to find the right software, be sure everything works. So via this other subscriber to my channel that I was talking to, etc., I started to think about this other device here, and that is then the Anritsu MG3700A that I eventually purchased. And this device has ARB as a standard. It is an ARB device. It does not synthesize. It only works as an ARB device. You can find it on eBay still rather easily, I would say. I think on average we'll be paying a little bit less than 1,900 euros or so for a device. And I'm later going to talk a little bit about the specs and compare it. But this seemed to be the most interesting option for me, basically, to get into the domain of ODFM and other type of modulation methods that were not supported by the two devices I already have. I ordered this device a month ago or so, and it arrived from Japan, and it really felt it was like in a mint condition. It was very nicely packed. There was even a box with it, with the original computer software with it, with actually the original compact flash card and adapter that was also shipped with the original units. It's fairly small at 256 megabyte. It came with a Japanese plug and with a Japanese earth prone. Those that have been in Japan might know that the Japanese houses and office buildings often don't have an earth socket installed. There's a whole story about this, but we're not going into that. So you do it by this additional wire here. Yeah, it came like a complete set. It really felt it was very well taken care of. And like I said, my unit was in a mint condition, even though later when I turned it on, I found out it did already have a fair amount of hours it has been running, I found in the system log. Now, a couple of important performance characteristics will be the sample rate, the system IQ bandwidth, and of course the amount of memory in which you can load waveform files. So let's go and take a look at that. If you look at the sample memory, and I'm showing here the 3 devices in the same order as my previous pictures, that one of the SMIQ is sample rate, sorry, is very limited. I think it's some 10 or 15 megahertz sample rate or so. Of the MU is a little bit higher at 100, but the Anritsu goes all the way up to a sample rate of 160 megahertz. So it's clearly basically the superior device in that respect. Then if we move to the IQ bandwidth, which is actually the bandwidth by which the modulator can be modulated, putting basically our baseband data up to an RF carrier, and here the SMIQ basically was in its best mode using an external generator, I think some 60 megahertz or so. The MU even a little bit lower than that, and again the Anritsu really much better specification. Internally, I think 120 megahertz, and when fed with an external IQ signal, it can even have a bandwidth of 150 megahertz. So that is really very good, even taking into consideration that it is all basically then the MU over here. And then when it comes to the amount of sample memory, then the difference is even going to be bigger. Here you see the SMIQ, and I'm not showing the numbers here, I got them somewhere in another table, but it's really small. You can add some additional memory here, but you can even see it hardly on the graph here. The MU can basically go to some 200 megabytes of sample memory. I'm expressing this as megabyte, so a byte of 8-bit. So if your word will be stored as a 16-bit thing, then the number of basically symbols or words you have that is half. And you have to cut it in half again if there's a separate I and a Q channel, obviously. But anyway, the Anritsu goes as a standard already, is sold as 1 gigabyte, so 1000 megabytes, and I'll skip over the precise gigabit thing here just for convenience. 1 gigabyte of memory, and it can be also bought in an upgraded version with 2 gigabyte of memory. And actually that's how my unit came, with 2 gigabyte of memory. Now on this graph it's hard to see these enormous differences between the devices. If we would be showing this basically on a log scale, then we still got an impressive difference of magnitude differences between the memory of the devices. So altogether, spec-wise, if you're interested in basically playing back arbitrary wave files for vector signal generation, I think the Anritsu really is a very nice offer. Now I would like to go a little bit more into the specific implementation of the device and first look at the inputs and the outputs that it offers. And obviously it got an I output and a Q output. Well, maybe not obviously. I mean, it could have just had an RF output, which is of course it does. And this device goes up to 3 gigahertz RF. And it can be upgraded, or there was an upgraded version that goes up to 6. On the signal path, actually, you see a nice repair video of that one where the 6 gigahertz unit was faulty. Actually, I think it never got completely repaired in that video. I don't know if Jerry managed to repair the thing altogether. But anyway, the I and the Q signals also come out of the device separately. There are also differentials, so you got a not I and a not Q coming out of the device. This is also standard. And you got I and Q inputs as a standard on the input of the device, on the front panel, sorry, of the device. If your I and Q would have been coming from something else and you just want to modulate it, taking advantage of the wide modulation bandwidth of the device. The only thing here that I could be complaining a little bit about, and other people have complained, is about the I and the Q outputs, the differential outputs. They're on the back of the device, But actually they're not 4 BNC connectors. That would have been really the easiest way. No, they have some 15-pin D-sub connector with the signals. I mean, it is not so much of a big deal, and I eventually made this little cable here with 4 pigtails and try to shield it properly. Yeah, I'll be trying to show a picture of this cable here. But it's still a bit of a convenience. I really wish they just would have fitted 4 BNC connectors. That would be just so easy. So I don't know why this particular design choice. All the rest of the connector basically is unused. It's all ground lines. Now back to the connections on our device. So these are basically the data and the RF signals. Then next to it we have a fair choice of trigger and sync type of signals. So on the input side you can input your own sample clock to the device in addition of just using the internal sample clock. There's something interesting about it and something important about it, and I'll get back to that later in quite a bit more depth about this input. There is a start trigger of the front of the device where you can basically have a complete pattern being started, and you got a pattern trigger as well where you have particular sequences started. So that makes it quite flexible. We also, as usually, have a 10 megahertz reference input if you need a better clock generator, a reference generator that's built into the device. You can also, as an option, have it with a Rubium clock, but I don't have that. But anyway, you can connect an external one. It can be 5 or 10 megahertz. The nice little touch about it, by the way, that you don't have to go to the settings to select it, but whenever it sees a signal coming in that is close enough to 5 or 10 megahertz on that particular input, it automatically switches to it, which I think is a nice little touch. On the outputs, well, the 10 megahertz also come out of the device. That's a common thing to have. But more importantly, there are 3 different outputs here, labeled AUX1, AUX2 and AUX3. And these are basically used to output particular markers that are related to your waveform. So you can set particular markers in your waveform, and these are super useful in order for further analysis and processing of the signal. And also get into that at more depth. The funny thing, by the way, in the manual, they specify these 3 lines as inputs and outputs, but I haven't come across any application where they actually serve as inputs. So maybe that was for future extensions of the device. I think as the firmware of the devices, they actually only serve as outputs. Then we also got built in as a standard. That also makes it very interesting, a bit error analysis, and that got a couple of inputs related to it as well. To be honest, I haven't got to that yet. There's so much to discover about this device that might actually become the topic of some future video or so. But we got a couple of inputs related to that. We got a couple of control inputs related to the RF signal. So we can actually turn it on and off from externally, and we can connect an external power sensor if we want the automatic leveling in the device to be even more precise or measured at a particular point instead of at the output connector of the device itself. And this is the internal circuitry to ensure that the output level actually meets the setting that you have tried to set yourself. And finally, there are some communications. There is a 100 megabit per second Ethernet connection, and there's a GPIB connector there. The Ethernet connection is rather important because we talk about waveform memory here. We have to bring waveforms to the device, and for that you either need to use the Ethernet or basically the memory card here on the front. And later also I'll show you a little bit how we do that, and actually they choose a quite nice implementation, I think, to get this all working. I want to talk a little bit about the usage modes of the device. Now we really get to the core of how the device works. So you can use it in basically 3 different ways. You can use it as a standalone device. So in this case you simply play back waveforms that are already on the hard disk of the device. And actually there are almost 400 waveforms that already come as a standard with the device. The second possibility is that you use a piece of computer software which is called IQ Producer that you get with the device. I actually got my my version has already mentioned it when it was shipped to me, but you can also get it from the Anritsu website once you register your device. And this allows you to create your own waveforms. They can be generic type of waveforms, like with a TDMA structure if you wish, with a multi-carrier, multi-tone, types of noise, but it can also be on the basis of standard telecommunications protocol like 2G, 3G, 4G, Bluetooth, wireless LAN, and so on. And the final possibility is that you really want to create waveforms yourself, and you can do that in a program like MATLAB, write code in Python. I actually did both, and it all works now with the device. And even if you wish to with Microsoft Excel, and I also did that, just simply creating certain IQ waveforms, creating them with 10,000 value points, putting exactly the markers the way that you want to make them. You export them as ASCII comma separated values. You input them in this IQ producer program. Then you might choose anything additional that you might want to have there as filters, or set the sample rate, and then it goes to the device. And all of these three modes actually work really well. So in my field test, I want to start from the very basics. We'll just be starting up the instruments and loading some basic waveforms. So to do so, I obviously turn on the power button. I will go it through its boot procedure. And what we're seeing here, unlike some other instruments that I have, that it's not running in kind of Windows or Windows embedded operating system. This is actually a real-time operating system. This is VxWorks that is running here, and that is an operating that is also used, I think, on the Mars rover device and a lot of really time-critical type of applications. And this was also the choice that Anritsu made when they made this device. I think later on they actually moved to Windows type of operating systems, but this one runs on VxWorks. And quite interestingly as well, even though the device has a hard disk, the operating system resides on flash chips inside. So if I take out the hard disk, he goes through the complete boot procedure. He gets here, but he cannot load any files because the files are going to be on the hard disk. And we also got our cat here checking out the process, huh, Kiku? Now, this is the start screen. We see the frequency button, we see the level button, baseband, that's the menu we're in right now, and we have to start always with loading a waveform because that's the basis for anything that we will be doing on this device. Now, normally when you boot it up, it starts exactly in the settings where you left it when you turn it off, and this can be very, very useful. But for this particular purpose today, I reset the whole device before I start. That's very simple. Actually, restarting is just going here. I tell him to restart everything, and that's it. Everything is initialized, so I start from a 0 condition here. I also see some warning here, oven cold. No worries about that. That is the crystal. It's the crystal is in an oven to keep it a bit more constant, and that oven is just a little bit cold still because I just turned it on. This will go away in a little moment, that warning. Now the first step is always loading a waveform into the system memory. So I'm going to load a file from the hard disk to the memory. What I'm seeing here, that we got the hard disk here, which is half full and also half empty. I got a memory A, which is empty right now, and I got a memory B, which is empty right now. And I see packages. I can actually select a package here, and that package will kind of have files related to a particular standard or particular experiments or whatever you want to be doing. But I'm fine here. I'm right now in the GSM package, and I'm going to load a file which is going to be a NB8PSK. That is a 8-phase key shifting GSM signal that is used for GSM edge communications, for example. So I'm going to tell the system basically to load that. I'm going to load it into memory A, that's selected right now, selecting it, and I'm going to return to the main screen. I haven't got anything yet because I can have multiple files in the memory, and I still have to select which particular file from that memory I would like to play here. So I'm going to go to set. I'll confirm once more from which package, because I can have multiple things ready. And I got one file here, DSM 8PSK. And what I see right now, he loaded it, he played it for one single time, and now he's in pause mode. One of the really nice things here is that I get to see some details about the file. These are actually details that that Anritsu saved with its file that it created itself. So we get a bit more information of what it is. But if you create files yourself, and I show that in a later video, you can actually do that type of stuff yourself as well. Now, what else do we see here? Basically, we see a bit how the signal routing goes. It's still very simple here. We basically go here. We can go to an iCube output, but it's disabled right now, and we can go to an RF output. It's disabled right now because the signal is not playing. The output is already there, however. How do I make it play? I make it play with the modulation button, and what we see now, actually the routing goes to the RF output, and we're actually playing the file. Now, for our experiment, I'm not going to look at the RF output yet. I'm going to do that in a second, but I would like to look at the IQ signals which come out of the back of the device and for which I made some adapter cables. And if I want to see these IQ signals, I'm going to do that on the Keysight scope here, which actually looks like a dwarf compared to all these large 19-inch machines here. I have to go into this menu and enable the IQ output. Then push it well. And there we go, we already see something happening on the scope. Let's try to see if we can get a little bit better signal out of that. I'm going to use auto scale to see if the scope can make any sense of that. Let me just disable 2 channels here. And I do get to see already something that looks like a burst, and that makes total sense because DSM sends its signals in burst. It's not triggering perfectly yet. We're triggering on channel 1. I can see that right here. So I'm going to go to the highest peak here. Yeah, I think I'm getting a little bit of better triggering. It's not perfect yet. Let's keep it at this, and I'll tell you a little bit later a bit about that triggering part here. I'm going to, now we actually trigger better. I'm going to move it a little bit here in the middle. We had some false triggers here. I'm going to widen the signal a little bit. Yeah, there we go. I'm happy with it. So what we see here, we see an I signal and a Q signal. And we also see that a part from the signal is changing with every burst, and a part of the signal at the beginning, at the middle, and at the end. So that's the preamble. This is something mid in the burst, and this is the amble at the back. I don't know how you call that. And actually staying the same. This is very interesting because what we actually see is precisely how a GSM signal burst is being defined. It starts always with a fixed type of pattern and ends with a fixed type of pattern. And in the middle, we basically have a training sequence. And that training sequence basically allows the GSM receiver to see some known type of information, and from that it can infer what the characteristics of the radio channel are, and it can adapt to it, including the thresholds it's using. So it's actually a very advanced system, and back in its days that actually was one of the things that made GSM a more capable mobile telecom system. That's one of some of the competing standards like DMs and the PDC standards from Japan. This part, this training sequence that we see here, the way it is used, I think it's actually called the Viterbi coder, interestingly named after Andrew Viterbi, one of the founders of the Qualcomm company. Qualcomm was not involved at all with making the GSM standard, but it developed that technology, and if I recall well, his lawyers advised against patenting it, and so the people developing GSM could freely choose to implement that into their standard. So great, we see a GSM burst just as we would expect it. One of the nice things is also that the Anritsu as a standard also has differential outputs. With a lot of other devices, that is actually an expensive additional option here. And so I also connected basically the 2 differential signals to the scope. So what I'm just going to do is that I'm going to disable 1 and 3. So we see the I and the not I, the inverse I. And we see the inverse I is exactly the opposite of the I, and in the same vein, if I activate channel 2 and 4, we see the Q signal and the not Q signal, where the not Q signal, if you look well, is exactly the opposite of the Q signal. So far we loaded a fairly simple waveform, we started playing it, and we look at the IQ signals here. And later I will be looking at the radio spectrum. But before doing that, I would like to look a little bit more at synchronization signals that are available in the device. Now in the waveform I'm looking at right now, I'm actually synchronizing my oscilloscope just from triggering on one of the IQ signals, which is fine for this burst. I'm still able to do it, but you can think of quite a lot of signals that are much more complex or actually continuous, in which you will not be able to do so. Now, one of the really great things about the Anritsu is that it has a number of different outputs that can be flexibly configured together with the waveforms. And you can use them for synchronization signals. And with the built-in type of waveforms, they're often pre-programmed with some of that information. Now, how do we find out about that? We can go to the manual. There's a separate manual on all these built-in waveforms. It's very extensive, but even easier, I can go to the external IQ setup menu, and I actually see here there's a marker 1 equal to the frame clock and a marker 2 equal to RF gate. Frame clock, basically, that is apparently linked to the frame that GSM is sending out. RF gate is apparently linked to the whole RF modulator being turned on and off for this particular signal. So they actually turn off the RF signal in this particular example. So we can take these outputs, they're on the back of the device on BNC connectors. Just going to return here. I wired them to the scope, and this is the first of them, the gate the burst signal. And I don't know if you can see it. It's very, very small. But this is a signal basically that basically just tells us for a very short time frame, a positive pulse here, that the burst has started, and the RF signal is in this case like the whole burst. So the RF signal is on. Let's try to focus on that signal a little bit. Let's bring it in the middle. We can make it a little bit wider. Yeah, and now we already see the problem with syncing. So what I'm going to do is I'm simply going to have my trigger on free source. There we go. Selecting it and choosing my trigger signal. And now I got a perfect trigger that is coming basically from the blue line here. And I'm now independent basically of the signal that of the signal itself. So even if this signal will be hard to trigger by itself, just using this burst signal here, and in this particular case I could also be doing it here on the red one because it happens to be the same, but yeah. So this is going to be very flexible in terms of being able to investigate the device or sync it to other devices that you later need to connect to. A couple of more words on what we're seeing right here, which I think is relevant. We're also playing it back at a particular speed here, and we can actually see that by going here to the advanced menu baseband reference clock. So it's playing back at a sample clock of 3.25 megahertz. And we see a number of samples per second, etc. So this is also information stored with the waveform. You can freely change that information, but it normally comes basically with the waveform as a preset. We can also do all types of stuff when it comes actually to trigger our own signal and trigger a particular repetition pattern in that signal, etc. It's something that I actually may get back to later. And while I'm looking at one specific signal now, actually there are a lot of different pre-installed signals available on this device as you buy it. Actually, there's an amazing array of signals of something like close to 400 pre-installed waveforms. And in this sheet, basically, you see a overview of that. We got a number of different cellular standards, 2G, 3G, 4G. We got non-cellular standards. We got a number of like TV standards, ISDB used in Japan, I believe, and DVB-C used in Europe. We got cordless telephony the personal handy phone system, also from Japan. Yeah, we can see this is a Japanese device. We find quite a lot of Japanese standards there, but also a lot of basically international standards and also standards in Europe, etc. We got Wi-Fi in various versions. We got GPS signals. We got noise type of signals, Gaussian noise, that's the one at the bottom, AWGN. So it's, this is really very, very nice. This just comes on the device as a standard in whatever version you buy it. And in later videos, I'll show you even get much more possibilities when you actually use this together with a computer instead of being a standalone device. Now, our Anritsu is not only a baseband vector signal generator, but it's also an RF vector signal generator. So we got an RF output and it can modulate signals all the way up to 3 gigahertz. There's also an 6 gigahertz version. I don't have that. So we're going to test that. I connected up my spectrum analyzer. There is just a DC block for protection in between, and I'm still at the same waveform signal, the bursty GSM 8 PSK signal. So what I'm going to do here is now basically turning the device on, and I see a carrier here appearing. Spectrum analyzer is still between 0 and 3 gigahertz here, and I'm actually going to modulate my signal. What I see now is actually it's a very narrow signal. It often disappears, and because this is the nature of this bursty signal, and this is not a real-time spectrum analyzer, but anyway, I see the nature that the signal most of the time is not there. It only comes there in bursts. So what we'll actually do, and we got so much to choose from, I already prepared it. I'm also taking a similar signal here, a GSM 8 PSK signal with a pseudo-random bit code of 9, which is continuous, not bursty. So I'm going to select that one, and what we see here, a continuous signal. See a bit of a spurious signal here. That might be that I'm overloading stuff a little bit if I turn the level down with a little bit, say to minus 10 dB. Yeah, then I don't see these spurious effects anymore. By the way, in terms of level setting, as you can see here happening, let me just go here. If I go above a certain value, like it's going to be here, 3 dB, then actually the device says unleveled, and that means that I'm in a kind of a over value range in which it still generates signals, but it might not be within its specifications. If we go lower than 3 dB, basically, we operate within the specifications of the device. So this is, of course, very simple, what we had expected. Now I want to go to some experiments where I think this unit really shines, and that is that it can play 2 waveform signals at the same time. So let's quickly go and do that, and we first have to select signals that we're going to load into the memory. So we go to these packages of all types of waveform, and to take benefit of the wide bandwidth of the signals we can generate, I'm actually going to take broadcast signals. I'm going to take digital TV broadcast signals. So we got a number of different of these signals included with the pre-installed again. You don't need any license in the unit. There are a number of standards here. I think ISDB terrestrial that is used in Japan, I think also in the US, not sure. And we got one here called CATV NXC. That is actually the European digital television broadcast, DVB, and then actually in the C version, the cable network version, so DVB-C. So I'm going to choose that thing, and I'm going to load it into the waveform memory, actually waveform memory A. And for waveform memory B, I'm going to actually select a other signal. Let's just take one of the Japanese digital television signals, selecting it. So both of my memories A and B actually have now a signal ready. Now returning here to the main screen, how do I get to play 2 things at the same time? It's actually by, oh excuse me, that's the wrong button. It's actually by going to the pattern combination mode. So we get to see a very nice screen with 2 different pattern players, their relative power levels, the way in which they're combined, then whether that goes to the constant wave carrier and the IQ outputs and everything. So let's simply start by loading a waveform into the first piece of memory. Yes, that is the thing that we were at, the DVB signal. and we got it playing right now. The output is on, nothing is modulated yet, but I don't see anything yet because we're still at minus 140 dB. So let's put it at minus the level, sorry, at minus 10 dB or so. Yeah, and we see our carrier waveform arriving here, unmodulated, and we're going to go and modulate that signal. And yes, this is the type of signal that we will be expecting, a relatively broadband signal. Now, I can determine the bandwidth of the signal by putting some markers over there. I can also do it automatically on the FPC 1500. Let me do that, and let me also use a little utility that I sometimes use myself, but I don't think I've been using it in videos yet. And that is actually by using my iPad. There's a special program on the iPad. It's called the Rohde Schwarz Mobile View, I think, and we can actually connect to the FPC. It goes very fast. And you see here we're getting the signal, the live signal right in, and I think it will even kind of, you know, adapt the signal to the orientation of the device. And this way we get to see the signal. I mean, I think the update rate is quite okay. You might see it slightly slower than it's actually on the screen of the device, but I think it's definitely quite workable. Now, I might be using this a bit basically to be able to give you a zoom in on the actual screen of the spectrum analyzer. Looking at the automatic measurement of bandwidth of the device, and that is actually implemented here in measurements, measurement modes, and we got a occupied bandwidth. You'll see it's the same signal. He optimized some of the settings for this specific type of measurement, and we now get to see the bandwidth is about 5.5 megahertz. Why do I say about? This mode is actually a very precise measurement of how much of the power of a signal resides in a particular bandwidth. But to do that precise measurement, we must actually already preset the known bandwidth of the channel. Now it's at 3.85 megahertz. That's the default value of this device. That is actually a wavelength that you find in wideband CDMA 3G signals. But should we want to measure this, and if we already would know that the bandwidth of this signal is, say, 6.1 megahertz according to specification. I don't know if this is right. This is just a value I'm making up. Then now I will be making a proper measurement. This is telling us that 40 something megahertz basically contains 99% of the total power of that signal. If we want to know what is in 80%, yeah, we would see this gets a little bit smaller, the markers here, and the 4.2. I think the 99% is the most used type of measurement for this type of things. Because you really want to know that very little power is actually going outside the defined spectral plot here and goes into adjacent band and causing type of interference that we don't want there. So yeah, a nice measurement mode that we got in our spectrum analyzer. I'm basically just turning back to the regular spectrum management, spectrum mode here. And I want to look at the second signal, of course. So how do we do that? We do that basically by going to the menu for signal B, and I'm going to select a signal B here. And yeah, let me take that other Japanese signal that I got here. I'm selecting it, and we get an error message. This is important to understand, this error message, because what's happening right now is that we took two different source signals that were supposed to play back at a different sample rate. That sample rate comes with the waveform, and that sample rate should be correct if we want a proper representation of the signal. And since our Anritsu can only play back with the same sample rate for both of the waveform patterns, we have two options. Either we're going to modify one of the waveforms to make sure that it goes to the same sample frequency and is still a proper representation. I think you actually get software from Anritsu that can do that for you. I haven't tried it out yet, but I think it's one of the functionalities of the IQ producer. The second option is just ignore it and let it just play back the signal. But we know now that, and I'm going to do that, but we know now that my signal is not representative anymore. It's probably spread out in terms of spectrum. So we shouldn't pay any attention anymore to how broad this spectrum is. It's still the right signal, but it's not played with the right frequency. I don't see the signal yet, but again, this generator here is at minus 90 dBm, so I'm going to put it at minus 10. There we go, and we see a broader waveform coming in. Yeah, that's just great. But of course we want to see both of these waveforms at the same time. That's where things get interesting. So one more press on this button does the trick, A and B. And you can already see a bit that both A and B are present now in my spectral diagram here. And one of the really nice things we can do is actually we can change for a frequency offset between the two of them. There you go, you see frequency offset. So within the baseband domain, we can already move one of these signals to another frequency, and then the end result is going to be modulated all the way to the RF output on 1 gigahertz in this case. So let us go and try to see that and set a value. And wait a minute, I think I'm in the wrong menu right now. Give me just a second. Frequency offset. Yeah, the frequency offset can be, in this case, between minus 14 and plus 14 megahertz. Actually, this depends on the sampling rate. I've also seen that I can actually choose up to 50 megahertz. So the sampling rate, I think, determines that. But let's just take this 14 here. I'm making typos. 14.2, that's the maximum we can go here. Set it. Oh, 14 hertz. And look at that, we got both of our waveforms now with a frequency offset between them. So this can be really useful, have these two signals there. And what we can also do is basically play with the relative power of them. Now we already set the power of them individually, but we can also set the ratio of power. And with this ratio of power, now let me just move my cursor here to full dBs. You see, I can make one signal relatively weak compared to the other, or I can basically attenuate the other signal. What I think he's doing is basically maintaining the total overall output power of the device and only changing the ratio between them. And he does that by actually changing these two individual values that we saw before. Unfortunately here, this gray screen just masks the other value we got here. But if I take away the gray screen here, you can see that he went to minus 31 and minus 7 here. Yeah, so this is really a very powerful tool to be able to play back two different signals here. We could have, you know, two kind of desired signals close to each other and see how an amplifier or a receiver deals with such signals being just next to each other. We could have one of them an unmodulated signal that is considered a type of interference. We can actually choose to have one of them being a noise channel. Then of course we want to make sure that the sampling rate for the noise is also right, but we got tools that come with Anritsu that allows us to do so. So we could have basically noise in which we have a signal superimposed on it. There are all types of possibilities here by having two waveform generators. Again, I like the nice way in which the signal path is actually being shown here. I mean, it's all very basic, but it's very effective. Huh? The two signal generators, where I have an IQ output disabled right now, where I have an RF output, where I insert my own IQ signal. If I would like to document what I got going on here, I actually can make a screenshot. Can do that to the internal drive. I can also do that to a memory card. Yeah, that's a bit of a thing. When I bought the unit, it also came with a memory card and even a memory card reader for a computer. But that memory card didn't work what I shipped with it. And then later I got some problems with my own memory cards as well, until I found out what the actual reason was. If you use this memory card on a computer and you don't eject the thumb drive in a proper way, then actually you get an error message on this device. And when you eject it into the right way, then everything works as it should. You just enter it into the device. It takes a second to configure it, as it's called. And once that particular thing is configured, you can make a screenshot, for example, by pressing the button here and then the one over here, and we'll see saving a screenshot. We get a message. You actually have to push away that message just by any key. So I can get that file, of course, off that card, but also using a rather flexible FTP mode that I'll be getting to in later videos. Okay, this brings us to the end of this episode, where we looked at the Anritsu as a standalone instrument. But I will be coming back to this device because I want to explore more what you can do with it when you hook it up to a computer system, and that gives a whole lot of new possibilities, like creating your own waveforms, but also importing waveforms that you made in MATLAB or with Python code or otherwise. And we might even going to have a guest episode on that one. And I hope also in the future that I can come back to more specific functionality like the bit error rate checking that the device offers. But anyway, that's going to be for future episodes, and I hope to see you there.